Do I have capacitance problem? Not really. Is it?
I guess no, because it's
okay. Let's do capacitance. Okay. Because capacitance problem on one of these things might show up, right? Well, okay. Look at this. Look at this. I'm gonna have to point out and ask you, what is the capacitance of this particular node? Okay. So let's go with this guy here. Output node, of course. Okay. This output node is connected to diffusion over here. Diffusion over here was not a good color. Let's go with a, I don't know, blue color, some color. No, bad color, still unusual color. Okay, here we go. It's connected to diffusion of this transistor. Do you agree? And it's also, if you go around the whole thing, diffusion of this transistor. Okay. What are these guys, by the way? I don't know. It looks like this is 2x to me. That's what it looks like. This guy looks like 2x, which is, by the way, correctly sized, ideally, right? So 2x transistor diffusion will give you 2 C's here, 2 C's here. It's going to also give you 2. Is there any other things that this output node is connected to? Let's see, over here, and then over here, anywhere else? Let's see. Oh, how about this guy over here? How about diffusion on this P, and also on this P? What are the capacitances of it? Just looking at the geometry, they look like 4x each. So I'm going to get 4 C's here, and 4 C's there, 4 C's over here. And total of what? 12 C's for that output node. Okay, is that clear? Good question, by the way.
Professor?
Yeah.
Should the PMOS, the 4 C's, should be two?
I didn't hear you. I'm sorry. Your mic cut off.
Oh, I'm sorry. Can you hear me now?
Yeah.
I'm saying that should the 4 C's on the top for the PMOS be shared among those two?
Oh, do they share? And answer is, I'm sorry, unfortunately, they do not share. And the reason is because there's something in between them. Okay. There is this contact between them. Exactly how these guys are arranged is as follows. If you pull out the schematics, this is what it looked like. This is my output node, and this is 4x each, right? And then you have, you know, more like this. Okay, and we're talking about this particular node, and you cannot share this bathtub with this bathtub, and the reason is because they are separated by this contact, unfortunately. Okay, these guys are in some way actually, you know, sweet mates, but apparently this is like there's another entrance in between these bathrooms, like public hallway or something. So you cannot share those 2 bathrooms. Is that clear? Only when you have 2 transistors in series like this, that diffusion can be shared. And that brings to the following question. How about this diffusion right here? What is the size of this diffusion? It's 2 C's. Geometrically, when you look at it from the top-down view like this, it looks much bigger than one bathtub. It looks like really elongated, actually super wide bathtub. But we're going to just simply count it as a shared bathtub that's worth exactly 2 C's. Because they are shared between this transistor and this transistor. And that's what the book says. Okay? But the reality is if you have a shared diffusion like this, sort of spread apart like that, that's going to give you a heck of a lot more than actually 2 C's. Any more questions on capacitances here?
So Professor, for the capacitor, do we need to calculate, for example, I remember we have raised a Elmore delay example in previous lectures, I remember. So in this question, do we need to calculate the capacitance of these metals and also other different areas, like we have
okay, so there's a difference between this book and the reality. Okay, and I think I gave you like a small discussion where actually if you are trying to look for capacitance of anything, you have to consider all things below it. Well, in this case, actually, you got gate capacitance of the transistor, right? That's clearly 4 C's, right? You also have to consider whatever that's above it, which is actually this metal line going over that poly separated by oxide again, and that gives you capacitance. But we ignore it because, again, we just don't consider that in our book. In real extraction tools, in fact, the tools that you guys are using, it does consider all those overlays, all those things that are going over you and under you, or whatever the node, given node that you are, when calculating the capacitance. Okay? For our exam, we'll just keep it ideal.
Yes. So we might, this is one more step ahead. So we might like calculate, for example, the Elmo delay at the opposite. I remember the question I had was like, how did we calculate resistance where there's a junction? I know when the, for example, when the metal and the tree side cross each other, I remember there was a half of resistance or a half of capacitors at the node. So you might go through an example like this.
Okay. So if I give you, I mean, we did that closer to reality resistance calculation when we were doing the metal wires.
Yes.
But when we're dealing with a layout like this, we're going to ignore that. Actually, we're gonna only consider the resistance associated with transistors and capacitance associated with gates and diffusions for capacitances. Only for transistors, right? Transistors. For capacitance, only gates and diffusions. Okay? These are the only things that's coming into play when dealing with ideal layout. Okay? Or this fake imaginary layout, but that's what we got in the book. But if I give you some metal and ask you to calculate some resistance, we got to do it differently. Okay, I want to move forward actually. Well, so we got a bunch of questions that ask you to figure out the resistance just by counting all this, of course, the transistors on your way to VDD or ground, and that's relatively easy to do. And then we have a bunch of little questions like this. Okay. Now this is, I'm going to try to cut down on some of these questions, okay? But others are fair play, and the reason is because look at this. You should be able to answer this sort of thing without looking up the book. Come on. Transistor doesn't behave ideally. Or this double negative thing is coming into play. Okay, because of one of these things. Okay? And it says mobility degradation in high field, channel length modulation. That is, you know, non-ideal thing, right? This sort of non-ideal thing. Subthresh leakage, that's also non-ideal thing. Body effects, that's also non-ideal thing. It's every one of these guys. Okay? So I want you to review out that section where we talk about non-ideal behavior of transistors and just know it. And if you get stuck in the middle of, you know, maybe you can ask a question, what in the world is channel length modulation? And I could say, hey, look, your channel length actually varies because your gate voltage relative to VDS minus the threshold or plus the threshold is not going to be the same actually everywhere on your channel. And the point where pinch off happens actually vary. Okay, and that's going to give a different, of course, different current level, but only in ideal world, only in real world, not in ideal world. In ideal world, what happens during saturation? Your current is fixed, flat, right? So ideal world is kind of boring, but it's simple. Real world is where every one of these things do come into play to make that minute changes, minute differences in the current that we're trying to calculate, okay? So next thing that I want to show you is, well, that's just, you know, I'm not even sure if I should ask you this kind of question, because now I have to, you know, look at it and then remember, hey, wait a minute, what the heck is this? Okay, well, it looked like current expression because we got gain here, and then with the VDS, yeah, sure, VDS, you know, what kind of equation was this? What was this? Anybody
Try the
remember?
region.
Huh?
Try the region. Current of transistor in the region before saturation, right?
Is this saturation?
Before saturation, trial, called trial region, or I'm not sure what's the name.
What if I just keep the same thing and then tweak it around a little bit? Let me just say, let me just keep everything, and then instead of putting VDS over here, how about if I just put VGS over 2, okay? Are you gonna be able to recognize this and say, it's, you know, that's one of the ideal transistor current, okay? If you do, that's awesome. It means you memorize your equations, but I just don't want to do that, okay? So don't expect to memorize this sort of thing. If you ask me, I'll give you non-ideal transistor equations. Okay? But know that there are 3 equations. First one is always easy, 0. Okay? But 3 non-ideal, or 3 ideal transistor equations. And anything that deviates from those guys, you have non-ideal situation. Like this, look at that, look at that. This is saturation. So we have a linear 0 saturation, and then there's just saturation, but it's still modified a little bit. Well, how is it modified? Channel length modulation actually comes into play here. But again, I'm not going to ask you to regurgitate this expression in any way. But if I give it to you, maybe you should be able to recognize it and say, oh yeah, that's how the channel length modulation modifies the current, source drain current. All right. And these kind of questions, I mean, you're not going to get same questions, but you're going to get a couple of the short answer. It's not short answers, it's just multiple choice, kind of subjective, objective questions. Okay. That's going to be sampled from all over the place. And hopefully not so much based on memorizing things, but rather based on concepts. Okay, that's end of exam number 1. At this point,
is this exam number 1 form shared with us on the drive, or?
no, I will not share this.
Okay.
Okay. At this point, I want to open up actually and take on some random questions from you guys.
Could we go over the Elmore delay problems from quiz 13?
Quiz 13, yeah, sure. We can go through any one of these quizzes. My Google Drive is a little slow. There we go. Quiz number 13. Oh, this is not. This has nothing to do with the Elmore stuff.
It's at the bottom, the Elmore delay stuff.
Oh, that. Okay, yeah, sure. The problems on the bottom has more to do with actually line or wire modeling. Okay, and then once you model a wire, you can use Elmore delay to actually solve them, and that's exactly what this is. And we'll do an example. Okay, and let's just do this. We can do T or pi. Choose one or the other. Once we do one example, you can probably look up the model difference from your notes and probably be able to do the other one yourself. So I'm just going to do one of these two. Tell me which one to do. T model or pi model?
Could we do pi?
Sure. So here we go. So let's pull out a pi model. You guys remember what pi model looks like? Each one of the segments consists of RC units, and this is what pi looks like. That's a line segment, okay? That's a line segment. Okay. And how many segments do we have? We got 3 of these guys. So here's one, and here's your 2, okay? And then here's your third pi model. And guess what? We have actually, I forgot to put the cap that goes with that middle one, right? So that middle one has 2 caps. Every one of these pi guys have two arms, essentially. You guys see this guy with the 2 arms, this guy with the 2 arms. And their shoulders are glued. Their shoulders are glued. Okay, and that's what we got. That's 3 pi's, okay? And then let's finish this picture by sticking in the ideal inverter. Ideal inverter means we have 1 R, right? You agree that we got 1 R going down to ground or VDD, it doesn't really matter. Okay, whichever. Output of that ideal inverter has how many R's? You tell me.
3C.
3 C's. Did I say R's? This one is 1 R. This one's 1 R. 1 R. 1 R. This is 3 C. How many C's is this, by the way?
1/2.
Exactly. Why was it 1/2 C? Because if weight of both of your arms combined is C, then each one of your arms worth half a C, right? Those 2 guys are together, by the way, right? They're dangling on the same shoulder that's shared between these guys. So I'm just going to call it, just C, 1 C for the whole thing. 1 C for the whole thing. And then here's another C, 1 C for the whole thing. And output, look at this. Output is terminated by 1 C. Okay. And we have basically 0.5 C over here, and then 1 C here. And that makes the capacitance of the output node how many C's?
One and a half.
Exactly. 3/2 C's. Okay, that's the model. Is this model clear to you guys? And I think you can do the similar if you take a T model. T model just look like this. Here's your T. Okay. There's a one C actually smack in the middle. Okay. And C this time around kind of becomes your stomach. Okay. And then you got an arm, and that's gonna join with actually other arms of the neighbors, and so on and so forth. Is that clear to everybody? So if this is half an R, and if this is half an R, this is equivalent to just basically 1 R, right? 1 R here in between these 2 guys, right? Kind of similar way there for our pi model, we have 1 C between each segments. You had a question?
I was still a little bit confused. How do we determine the capacitance of the capacitors in the pi model? Could you briefly go over that again?
Okay. It says each consists of 1 R and 1 C. In pi model, by definition, looks like a pi. There's a resistor in the middle, and there are 2 caps, 1 on each arm, just like that, or 1 on each shoulder. Okay? And this, the entire resistance has to equal to the R, which is 1 R, because that's given. And these 2 guys together must equal to a C. Therefore, I'm going to have half a C here, and then half a C on the other side. Okay, that's all. That's all we're using.
How do we get to 14.5 again, Professor? Do we just add up all the C's?
Let's do that exercise now. Now that's the Elmore part. Okay. So far, we came up with a model, or actually, we used this component model to compose this entire circuit, right? Equivalent circuit for this description. Okay. Now let's do Elmore model.
Professor, how do you get 3 C's for the inverter?
That's the output of an inverter always. Ideally sized inverter always have 3 C's.
Okay.
All right, now I'm going to try to do RC on this whole thing. Let me point out the nodes first. Here's my node. Here's my node. Here's my node. And here's my node. And I have to do just 4 RCs and add them all up. Okay, no big deal. Okay. What is R for this guy?
1.
1. How many C's do you see dangling on this node?
3.5.
3.5. Perfect. Plus, let's do the next one. What is R for this guy?
2.
2.
Is it because 1 plus 2, is that why?
No, to the left from the inverter.
It's because if you're getting any charges or if you're getting drained to ground, you'll be heading out this way. It's either hooked up to VDD or ground, right? VDD or ground. And your pathway to your source is this way, okay? So it's going to be 2 multiplied by, how many C's do you see here? Total.
1.
Perfect. And then how many R's again on this guy? How many R's on this guy? How many C's here? How many C's over here? Oh, let's see. Oh, I just did that actually. 3 over 2, right? Or I'll just say 1.5. You guys want to add numbers together here? 3.5 plus 2 plus 3 are 5, 8, 8.5 plus, shoot, a big number. 8.5 plus, you guys want to do this math with me?
6.
6. These, is it 4, is it 15.5?
14.5.
I don't see 15.5 here. So I must have goofed it up. It is 14.5. I mean, okay, so here's a thing. Okay. I hope you guys don't need calculator for this kind of problems. Your additions, multiplications will be limited to actually something of this complexity. So unless you're a 55-year-old man who forgot how to do additions and multiplications, I'm going to ask you not to use calculator. Is that okay? Yeah? All right, I hope that answers that question. Any other questions you're gonna deal with?
I'm still a little confused. Where did the 2 come from to multiply by the 1 capacity, and where did the 3 come from?
For this node, your resistance of the path down to the ground is 1. Okay. For the next guy, for this guy, your resistance for your pathway down to the ground is 1 plus 1. Okay. And the resistance for this node down to the ground is 1 plus 1 plus 1. Okay.
Okay, thank you.
Okay. And so on. That's a good question. You must, that's Elmore. That's the crux of Elmore. You must know how to do that. It's not fair for me to, I'm not going to answer if you ask me that question during the exam. It's a good thing that you asked now.
I have another question. Where does the very last capacitor come from after the third segment? The 1.
Although this guy?
Yes.
Oh, because it says terminated by 1 cap.
Oh, okay. All right. Thank you.
So yeah, make sure you read them out carefully. Okay. All right. Any other sort of material that you guys want to talk about, go over, etc., before we close?
Professor, can you solve the wire capacitance problem of the same quiz? It's about.
Oh, you mean one of those problems up there? This sort of thing?
Yeah, this one and the one below.
Yeah, we can talk about this. Okay, it says for this one, how many C's do you have? And I just went to the picture, actually, the geometric sort of layout, 3-dimensionally, of what we got over here. So if the length of this square box is exactly 1, what we're looking at is actually a cubical looking thing, right? And the question is, what is the resistance from face to the backside of this cubical looking thing if it's surrounded by other material? Okay, by other material. But and what is given is actually for each one of this unit capacitance, unit capacitance is going to be 1. So 1 here, 1 on the other side, 1 on the top, and 1 on the bottom. You're going to end up with a total of 4 units worth of capacitance. That's easy to see, right? Right?
No.
Okay. So every unit coupling capacitance of the shaded wire is C, and in total, how many capacitors do we have if the wire size is 1 by 1 by 1, which gives you exactly a cube. And what we're doing is we're trying to figure out the capacitance of this wire. That node, looking at that particular electric node, there's a capacitance with this neighborhood, because all this area is oxide material or dielectric, because you have a separation in your device with the oxide between all the conducting layers and traces, right? And you also have a coupling capacitance on the side, just like that, and so on and so forth. Okay, so you have 1, 2, 3 units worth of capacitance. Okay, is it still not clear?
Yeah, that is clear. Thank you.
Okay, Now we're going to take, so remember this image. Remember this image. And we're going to go down to actually next problem, which asks you, okay, now your device, size of these things have changed. And your new device look like the following. It's 1 unit in width and 2 units in length. So I'm going to try to draw it as proportionally as I can. Okay. And then it's 3 units tall. There you go. Dot, 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 dot. If you can imagine this 3-dimensional looking little piece. Okay. And what we have is actually capacitance. Again, on the top, on the side, and on the bottom. And what is the total capacitance? That's the question. Okay. And the field of view, the electric field of view, you know that from physics, right? It's just simply the size of the exposure geometrically. And the top, I note that it has exactly same area as twice this cube, because that's how it is given, right? That's how it is given. It's 1/2. That's what it says right there. Okay? So that's going to get you 2 C's this way. Same thing on the bottom. It's going to get you 2 C's. How many C's are you going to get on the side, by the way? The area of the side is going to be 2/3. As a result, you're going to end up getting 6 C's, 6 C's here. And the whole thing together is going to worth 16 C's. Is that clear?
Yes, thank you.
Any other questions on this?
So which lumped element wire model is most accurate?
Yeah. I want you to be able to answer that kind of question.
A brief explanation would be great if that's okay with you, Professor, but otherwise.
For that, I want to ask you to listen to that lecture where we have wires. There's a lecture on wires. In that lecture, I explained to you each one of these models and which one is best.
Yes, sir. Thank you.
And it's also shown on the slides. Okay. Any other topics?
I was wondering if you could talk about the relation between logical effort and parasitic delay. Quiz 10, if you wanted to have some later questions to look at.
Sure. Since we did this one already, let me just give you some random other problem. How about that? Okay. Let me see if I can draw some crazy looking picture here. And I'm not even gonna have a actually ideal model for this one. I'm just gonna come up with some. I'll just do an ideal model. Just can't make up my mind. What if you're given something that looks like this? There you go. And you guys know how to do the NMOS for this circuit? That's how you do it. Okay. Now, what is logical effort for this case? Okay. You know, it's always divided by 3 because we're comparing it to an ideal inverter input, right? Ideal input will always have 3. 3. Something divided by 3, something divided by 3, something divided by 3, and something divided by 3. That's what we're going to get for A, B, C, D. Okay? And here are the logical efforts. Look at A. What is the capacitance on your input? Before you answer that question, I think you should just annotate each one of these guys and say, hey, this should worth 2x. This should be 2x. This should be 2x, 2x, 2x. Oh, how big should this be? Help me.
6.
Well, 6, exactly. There you go. Okay. So what is the input capacitance for A?
4C.
Exactly. Logical effort for input A is 4/3. For B, it is, let's look at B. How many C's for B? 2 plus 6 on the other side. Yeah? 8. 8 here. 8 here. Is that clear? Is that something you can do?
Yes.
All right. So if you're happy about it, you can sing, hopefully mute it. And we can go to the next problem. Parasitic delay, okay? So let's talk about parasitic delay for the same problem. The same circuit. Parasitic delay is comparison between actually the cap here. Parasitic delay is the cap here, that point, divided by cap of the output node of ideal inverter, which is again 3. Okay? So you tell me what the cap is for this output node. Let's see. You have 2 worth of diffusion here. You have 6 worth of diffusion here. And downside, you have 2 worth of diffusion. Total of what? What is this number?
10.
10. Exactly. I'm going to put 1 0 on top. 10/3 is parasitic delay. And that is in terms of actually RC. Okay? And these guys are just proportions, right? So it's just effort factors. That's about the
So-
extent. Yeah, go ahead.
In general, the logical effort is comparing the inputs to an
Yeah.
ideal inverter, and
Uh-huh.
the parasitic delay is comparing the output.
Exactly. So in some sense, the logical effort has to do with actually, if someone's pushing you with a signal, how strong does that signal have to be to actually make changes on this guy? Remember a long time ago, I gave you an analogy. You have a bunch of gates kind of standing in a row, and every one of these gates is going to try to push over the guy in front of it, and then that's going to propagate forward. And logical effort has to do with the size of your hand, or actually how difficult it is to push the guy next to you. Okay, and then parasitic delay is kind of equivalent to the weight of the person. If it's like a strong, tall person in front of you, and if you're like really skinny and short, it's going to be very difficult to actually move the next person, right? The weight of these gates matter, and that's the parasitic delay. Okay. All right. Any more questions? About the exam, about any material? Uh-huh. This one? Yeah, okay. There we go. What you have to do is actually figure out logically what each one of those variables is going to do over a period of time. What period of time? A period long enough so that actually all the signals involved in the circuit is going to repeat. And that happens to be 16 clock cycles. And the reason is because it's hooked up to actually 4-bit counter. And you know that, right? So there are two ways to do this sort of problem. One is to draw actually timing diagram, schematic. The other one is actually just laundry list the binary combo of what's going to happen on each one of these guys. So let's do the combo here because I can type easier. A, B, C, D. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, oops, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1. And then it goes back to 0, 0, 0, 0, right? So I'm going to consider the 16 clock cycles as a repeating period, okay? Now, what we're looking for is alpha is the probability that your signal is going to actually change during a clock period or half a clock period. Or your signal is going to go up and down on a clock period. So what I would do is look at the circuit and find out what's going to happen on every one of these clock cycles, what's going to happen on my output Y. And oops, and maybe you can help me. What's going to happen to Y if your input is 0, 0, 0, 0? It's going to be 1. It's going to be 1. It's going to be 1. Actually, I don't know. I'm going to put 1 everywhere for now. And say, hey, some of these guys are wrong. Okay? Can you tell me logically what my output's supposed to be? Or which one of those lines I got this guy's wrong?
So 0, 1, 0, 1 should be 0.
Yeah, well, let's do it this way. What is the expression for Y in terms of A, B, C, D?
D and AC or B in parentheses and the whole thing with a not.
The whole thing not.
The whole thing is,
Like that.
yeah.
But I'm kind of lazy to put the whole thing together, so I'm just going to use De Morgan's to do this. Is that okay?
Yeah.
Yeah?
So
Look at this. As long as D equals 0, my output's going to be 1. Do you agree?
yes, sir.
So I got the right answer for every other ones. Every even ones, or actually every even ones. Every other one, I have no idea. I was wrong, okay? There you go. Let's finish these guys. Is there other times when my output is going to be 1? Well, actually, when B equals 0, yeah, when B equals 0, do you think I'll get a 1? Look at it. Look at this expression. When B equals 0, you got something going on, and then something will determine whether you got a 1 or 0, right? Oh, how about if we look at it this way? When B equals 1, well, when B equals 1, look at this. When B equals 1, this is always going to be 0, right? So when B equals 1, blah, 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 like right here, I'm not doing this right. Someone help me out. Bail me out, please.
So it should be 1, 1, 1, 1, 0, 1, 0.
Like that?
No, just for the beginning. Like it should be 1, 1, 1, 1, 0. Yeah, 5, 1, and 1, 0. The first 5 thing.
0 here.
Yeah. And then 0.
Another 0.
Yep. And that's 1.
1.
And 0, 0, 0. Yeah.
Okay.
Professor, I
how
think
many go ahead.
I think the whole equation should be under par.
No, I think I'm okay.
There's supposed to be a plus sign after that first D bar, or is it not ANDed with everything? Oh, never mind, never mind. I see that.
You saying algebra. Okay. Whichever expression you use to cough up a bunch of ones and zeros over here. I think he did it right, or at least I'm gonna trust him. And I note this output signal goes up and down. How many times? How many times does it go up and down?
5.
Wait, so yeah, I actually have a question about like going up or down. Are we only, so in terms of like the timing diagram, are we considering the falling edge, or like are we considering the up and down motion, I guess?
It doesn't matter. We're counting 16 clock cycles.
Yeah, that
Your clock is gonna go up and down 16 times.
yeah, I got that. I got the 16 part, but like
So-
for the 5,
Mhm.
like which one are we exactly calculating?
Yeah, so what happens is actually if I draw a sideways diagram, it's gonna be 1, 0, 1, 0, 1, 0. It's gonna look like this, right?
Yeah.
And then it stays at 1. It's gonna go back and stay at 0, right? Stay at 1. Over 16 clock cycles, this has gone up and down how many times? 5 times. It's gone up, down and up how many times? 5 times. Same thing. Whether you're looking at up and down or down or up, same thing. Okay?
Oh, okay.
Now, that's how many times it made a full transition.
Yeah,
And
yeah.
if you divide that by 16, well, that's, by the way, your alpha. That's the probability that you will make a transition within a clock period. Here's your clock period.
Okay, so for the question up there, what does it mean by LSB? Like I know something about like
And most significant bit, least significant bit.
so so that means D is the least significant bit, right?
Yeah.
Okay, cool.
Okay.
Yeah, also following up for that, I think it's the next question, right? Where you calculate the dynamic power, yeah. Why is it 8? So do you just add up B, C, and like B and both D?
Okay.
Does it?
Okay, so this is the kind of things that I'm gonna do it slightly differently. I'm gonna actually give you the whole expression. Dynamic power equals alpha C V square F. That's what it is. And these two guys are given. Okay, these two guys are given. And we know how to do alpha. We know the alpha. Now we're gonna figure out C. What is the C for this circuit? Well, when you ideally size these guys, it's gonna be 2 here, 4 here. Well, I'm not gonna do the rest because I'm too lazy. This is gonna be 4. This is gonna be 2, right? So capacitance on this node is gonna be basically 2 plus 4 plus 2. That's total of 8. 8 is your C. Okay.
Gotcha. Yeah, that makes sense.
Then V square F. That's it. We're done. Okay. Let me also point out that please practice, not practice, but try to make sure that you can set up your cell phone or your recording or Zooming device so that you can do what I showed you. Actually, if you go to the shared drive and if you open up important instruction for the final exam, there's a picture. I'll tell you this information again on this email that I'm going to send everybody, hopefully tonight. You should be able to zoom a view that kind of look like this. I'm trying to show you this thing, by the way. I don't know why I cannot share. Just give me 1 second. This will be up in a second.
So we don't need to like upload any screen capture video, like.
No, you're not going to record. You're not going to upload anything, but you are going to use your phone or another device, whatever you want. You can to zoom like this. You see that? This is you. And I'm showing no headphones, no earbuds, no notes, only exam window must be open, nothing else. Okay, it's raining like crazy, so I gotta go out and close my windows and stuff. So we're gonna call that a review. Okay. Thanks for
For the exam, are we allowed to use scratch paper?
No. Oh, scratch paper. Yeah, scratch papers. Clean sheet of paper or sheets of papers. That's fine.
Okay.
So make sure your scratch paper is shown on this view. Okay.
Do we need to have two views set up? So you mentioned that we have like our phone like behind us. Do we need to also have our webcam in front of us as well?
No, just
one device.
Just this view. That's all
Okay.
you're zooming.
Okay, thanks.
Professor, if you don't mind me asking, like how much exam 1 material is going to be on the final?
How much stuff from exam 1?
Yes, sir.
I'll say maybe half.
Okay, thank you.
I gotta run out actually. It's raining like crazy. I don't know how it's. Is it raining everywhere? Do you guys hear the rain and weather going up again?
Yeah, it started raining real bad.
Yes.
All right. I gotta run out. So good luck. See you guys Tuesday. If you have any logistic questions, like where to find Zoom link, that kind of stuff, use email. But wait for my email before you ask questions about the exam. Okay. See you guys.